Welcome back to Easy Academic. This is episode 0 in the Linear Algebra 1 series. So what is linear algebra? Linear algebra is a branch of mathematics that deals with representing linear equations and functions. Using linear algebra allows us to handle large amounts of data in useful ways. And for this reason, it's useful in areas such as machine learning, data analysis, as well as almost every area of engineering, like physics, finance, and even electrical engineering. In the following videos, you will learn the basics of linear algebra, concepts such as vector addition, scalar multiplication, all the way up to matrices, and all relevant associated operations of them. If you have any questions or suggestions, be sure to leave them in the comments, and like and subscribe in order to see future videos as they come out. Thank you. Welcome to Easy Academic. In this episode, we'll be going over vectors, their definition, different forms of notation, and simple properties of vectors. So firstly, a vector is a mathematical object that's said to have a direction and a magnitude. So what this means algebraically is that, say we have a graph. If we create a two-dimensional plane with this point, 0, 0 as the origin, then we can say that a vector is sort of like an arrow, points in a specific direction, and it has a specific length, which we'll call its magnitude. So if we call this vector A, then we'll have coordinates x, y. So we can notate A as A equals x, y. This is likely the notation you're going to see if you're just referring to coordinates in the Cartesian plane. However, with vectors, we are more likely to notate it in this sort of column-like way. So you'd see it as x, y like this, where you'd have the first entry on the top, the second entry below it, and so on. And in 3 dimensions, you'd have something like x, y, z. So let's now take the example of a vector q. Let's say that vector q is equal to 2, 3. So how would we notate this on this graph? So first we'd find its x-coordinate, which is 2. So 1, 2. And then we find its y-coordinate, which is 3. So 1, 2, 3. And then we'd know that the vector starts at 0, 0 and ends at 2, 3. So we'd have something like this. So this is the vector 2, 3. Let's try now moving this vector around. So let's say we move this vector 2, 3 and start it at 0, 2, or sorry, 2, 0 instead of 0, 0. You'll notice that this vector is, it's functionally exactly the same, but we've changed where its origin location is. This is still fundamentally the same vector, but we've changed where we started it from. So does changing the vector change the actual value of the vector? The answer here is no. Let's look at some other examples. Let's now start with a vector A, which will make equal to 1, 4, and with a vector B, that will make equal to 5, 5. So if you're following along at home, I'd like for you to create your own plane and try to draw where these vectors would appear. So you can pause the video to try to figure that out. Okay, so first we'll start by drawing the vector A. And let's draw this vector A in blue. So if we have vector A in blue, we'll first start by finding the x-coordinate, which is 1, and then the y-coordinate, which is 4. And we'll observe that it starts at the origin. Just in the standard vector notation, we always start at the origin, and it ends at this point. So the vector points in this direction, and it has this length. If we start with vector B now, which we'll draw in red, we'll observe that it's at 5, 5. So the x-coordinate is here at 5, and the y-coordinate is here at 5. So we'll have a vector that looks something like this. Next, we're going to look at some alternate notations of vectors. So you might see vectors, as I've shown them, in this sort of column description. So for example, let's take this column vector 5, 3. Some people might write this vector as 5, 3, sort of similar to how you might see standard coordinate notation. Both notations are more or less valid if we are attempting to display something in a plane, but you'll see in future episodes why it's more conventional to write your vectors in this way. But just know if you ever see it written like this, you can still represent it in 2 dimensions if you treat, again, the first entry as the x, second entry as the y, or in 3 dimensions, you'd have the third entry as the z. Next, we'll be talking about vector magnitude. So the magnitude of a vector, as I earlier stated, is the length of the vector. So you might be asking, how do we compute the length of the vector? Well, let's say, for example, we have a vector A, and we'll make its value equal to 3, 4. So if we were to draw this vector out, we'd have x is 3 and y is 4. So we'd have a vector, let's draw it in red, and we'll have it look something like this. Now you might observe that thanks to the Pythagorean theorem, we could find the length of this line by finding the x-coordinates squared and the y-coordinates squared. So the magnitude of A, which is often denoted as with 2 lines, so this is how we say magnitude of A. Magnitude of A is equal to the square root of the x-coordinate squared plus the y-coordinate squared. So we'd have 3 squared plus 4 squared. And for the astute among you, you might observe that this is a 3, 4, 5 triangle. So we'd have that the magnitude of A is equal to 5 units of length. Let's take another vector, which we'll call vector B, and we'll make it equal to 2, 2. So if we were to draw out vector B, we'd find that in the x we have 2, in the y we have 2. So it would look something like this. If we now wanted to find its magnitude, and you can pause the video to attempt to find it yourself, we'd find that the magnitude of vector B is equal to the square root of 2 squared plus 2 squared. This is equal to the square root of 4 plus 4, which you'll observe is just root 8. So some instructors might ask you to find this exact value using a calculator. Others, in the case that you might not have a calculator, would just ask you to leave it in the form of a rational. So you could even simplify this further and find that it's equal to 2 root 2. Before we move on, I'd like to point out one more notational nuance that you might observe, and that is oftentimes when we denote vectors, we denote them using an arrow on the top of them. So throughout this video, I've been referring to vectors like A and B, just using the letters A and B. Since this is a linear algebra tutorial, it should be assumed that anytime I refer to any letter or any arbitrary value as a vector, it just is a vector. But if you were to see a letter or some other character with the arrow on top, it's safe to assume that it's a vector in most mathematical contexts. Finally, we'll talk about the concept of a unit vector. So the unit vector is any vector. Let's create a new vector and let's call it C. The unit vector is any vector where the magnitude is equal to 1. So C is a unit vector when the magnitude of C is equal to 1. So let's show an example using the 3, 4, 5 vector. So if we take the earlier vector, which we called A, and we have its value as 3 and 4, as we earlier proved, the magnitude of A is equal to 5. So if we wanted to make this a vector, be a unit vector with magnitude 1, what we do is we divide this vector by 5, because 5 divided by 5 is 1. So when the magnitude is 1, we simply need to multiply the vector by that same value we multiplied the magnitude by, which in this case is just 1 over 5. So if we now took A, 1/5 A, we made it equal to 1/5 3, 4. This is now a unit vector, because as we can show, the magnitude of 1/5 A is equal to 1/5 times the magnitude of 3, 4, which we already know to be 5. So the magnitude would be 1, and it's a unit vector. The final thing I'd like to show you is the standard basis vectors. And so what a standard basis vector in this context is, it's a unit vector that we can use to describe standard axes, such as in the xy plane. So for example, if we take the standard basis vector I, which we'll denote here with an arrow, we can say that this vector is equal to 1, 0. So that's 1 in the x and 0 in the y. Let's denote it using the color red. And that's what the standard basis vector I looks like. You might see this in physics or in calculus, and just know that it's used to refer to this vector, which goes 1 in the x direction. Let's denote now the second standard basis vector j, which is equal to 0, 1. And again, this is equal to 0 in the x and 1 in the y. So it would look like this. In higher dimensions, such as in 3 dimensions, you might even see a standard basis k, which would be notated like this. And note that since it's in 3 dimensions, you'd have 3 entries. So you'd have 0, 0, 1. And this would be a 1 in the z. And so this has been an introduction to vectors in linear algebra. Please like and subscribe to the channel. If you have any questions, be sure to leave them in the comments. And if you have any further topics you'd like me to cover, be sure to leave that in the comments as well. Thank you. Welcome to Easy Academic. In today's video in the linear algebra series, we'll be covering vector addition and scalar multiplication. The definition of vector addition in linear algebra is simply, say we have a vector A, and we say that vector A is equal to A1, A2, where these are the entries in vector A. And we say that vector B is equal to B1, B2. We can say that A plus B will give us some vector C, where C is equal to the entries of vector A pairwise. So what that means is that we take the first entries of A, so A1, we add it to the first entry of B, which is B1. We then take the second entry of A, A2, and add it to the second entry of B, which is B2. And so what does this look like geometrically? If we were to draw a graph in 2 dimensions, and create 2 arbitrary vectors, let's now assign real values to A and B. So let's say that matrix A is equal to 2, 1. And then matrix B is equal to -1, 3. So first, if you'd like, you can pause to attempt to figure out what matrix C would be in this case. So if we took A plus B, we would find that C is equal to 2 minus 1 and 1 plus 3, which is equal to 1, 4. And so if we were to draw matrix A as 2, 1, so again that's 2 on the x and 1 on the y, like this. And matrix B, we'll do it in blue, and that's -1, 3, so -1 and then 3 in the y, so something like this. And I'll just draw in some negative values, -1, -2, -3. If we were to add these two vectors, we should get 1, 4. And so what we get is this vector C, which is equal to 1 in the x direction and 4 in the y direction. And so when we draw it out, it looks something like this. And so what does this exactly mean geometrically? Let's zoom in to get a better look. So if let's erase this for some clarity. If we took our first vector here, which is 2, 1, and then on the head of the first vector, we're supposed to draw the tail of the second vector. So instead of drawing the second vector from the origin, we draw it from the head of the first one. And so what we do is we go -1 in the x, we go 3 in the y. And so what we find is that we get this vector. And as you can see, this vector is exactly the same. This vector right here is exactly the same as this vector, but we've just drawn it at a different position. So what we're doing when we're adding vectors is we're really taking one vector and just shoving it on the end of another one. And so if we were to draw C now, by starting from the first place that the first vector starts at, which is the origin, and ending at the head of the second vector, we find we have the exact same vector, 1, 4, as we did when we drew it from the algebraic method. Let's now take the three-dimensional example. Let's take the vector r, and we'll set its values to 1, -2, 4. We'll now take the vector s, and we'll set its values to 0, 5, -1. So if we now took r plus s, we'll find that it's equal to 1, 3, 3. Which, if you couldn't see that intuitively, it's 1 plus 0, -2 plus 5, 4 minus 1. With time, you'll be able to, with these simpler vectors, just add them up in your mind. And the same principle or property in 2 dimensions holds in 3 dimensions. So say we drew this out, we'd find that if we added this vector and this vector, what we would do is we'd add the tail of this vector to the head of this vector, and then find the resulting vector, and it would be exactly this vector, 1, 3, 3, in 3 dimensions. Now let's move on to scalar multiplication. So let's take the vector A. We'll set it equal to 3, -2. Now what scalar multiplication does, as I alluded to in the earlier episode, is that we've multiplied the magnitude of the scalar by a certain amount. So we multiply its length by a certain amount. So if we took the scalar value of 2 and we multiplied it by vector A, we'd find that 2A equals 2 times 3, -2. And you could write this mathematically as simply just the entries multiplied by the scalar. So 2 times 3 and 2 times -2. So we'd find that 2A is equal to 6, -4. Now geometrically, let's say we drew out, let's draw it in red. Let's say we drew out the original value for A. So we'd find that A is equal to 3 in the x and -2 in the y. So it'd be equal to this vector. So in theory, when multiplying by 2, what we'd find is that this vector that we get from this operation is in the exact same direction, but it's 2 times as long. And so let's see if that property holds. If we draw 2A in green, we should find that 6 in the x and then -4 in the y gives us this vector, which, as you can see, is exactly in the same direction as the original vector, but it's 2 times as long. If we take the same vector A, so A equals 3, -2, and we now multiplied it by a negative scalar. Let's say we multiplied it by -2. What we'd find is that -2 times A equals -2 times 3, -2 times -2. An interesting thing happens when you multiply a scalar by a negative value. So we find that the entries are equal to -6, 4. And so if we redraw the original scalar A, we'll find that we have 3 in the x, -2 in the y. What happens now is that the resulting vector from multiplying by -2 is pointing in the exact opposite direction. And so let's see if that holds true. So what we have is -6 in the x and 4 in the y. And so as you can see, this new vector points in the exact opposite direction as the original, and it's 2 times as big. Say we multiplied it by -1, it would just point in the opposite direction. And so what scalar multiplication does is it can make things point in opposite directions, and it can magnify the magnitude of a vector. And so this brings us to introducing the idea of linear combinations. So what happens when we combine vector addition and scalar multiplication? Let's say we have a vector, again A, and we set its value equal to 1, 2. And say we have a vector B whose value is equal to 4, -1. A linear combination is every possible way we can add A and B while multiplying A and B by some scalar values C and D. And so what this looks like algebraically is we'll find some vector x, which is equal to C times A, so C times 1, 2, plus B times D, so plus D times 4, -1. And so what happens is that you can find any value for C and D, and you can multiply it by these two vectors, and you'll be able to get any value x. In this specific case, an interesting thing happens, which is that A and B are not parallel. And so what that means is that they don't point in the same direction, or they don't point in exact opposite directions. And so what happens is that since these two vectors are not parallel, you can obtain any point in the xy plane. Let's say we had a new vector b, which was equal to 2, 4. What you might observe is that this is equal to 2 times a. Since a is 1, 2, if we multiplied it by 2, we'd get 2, 4. And so since it's equal to 2 times a, that means the two vectors are parallel. So if we now took this new b and multiplied it by, and took d and multiplied it by it, what we'd find is that every possible linear combination of a and b, so any value of c that we multiply by a plus any value d that we multiply by b, will simply get us a line, and that line has the direction equal to a or b. And so this is a preview into the concept of span in linear algebra, which we'll explore in a future video. If you have any questions, be sure to leave them in the comments. Thank you for watching, and be sure to like and subscribe for more related content. Welcome back to Easy Academic. Today in the linear algebra series, we're going to be going over the topic of the dot product. So the dot product of two vectors, let's say vector A and vector B, is denoted as A dot B. And so what this means algebraically, let's say A is a vector in 2 dimensions. Let's say it has entries A1, A2. And let's say B similarly has entries B1, B2. If we took the dot product of A dot B, which would look something like this, what we'd be doing is we'd be taking A1, multiplying it by B1, and then adding A2 multiplied by B2. And so what we'd have is A1 B1 plus A2 B2. And as you might imagine, for higher dimensions, this trend would continue. So let's use an example in 3 dimensions to illustrate this point. Let's say we have matrix A, which is equal to, let's say it's equal to 2, -1, 3. Let's say we have matrix B, and we'll set that equal to 4, 0, -2. If we took A dot B, which is equal to 2, -1, 3 dot 4, 0, -2, what we'd find is we'd first take the first entries, 2 and 4, multiply them, add the second entries, -1 and 0, and then add the third entries 3 times -2. So what we'd have is 2 times 4 plus the second entries, -1 times 0, plus the third entries, 3 times -2. And so what we'd find is that A dot B is equal to 8 plus 0 minus 6, which is equal to 2. Let's now take another example where we'll set A equal to 1, 2, and we'll set B equal to 2, -1. So if we now attempted to take A dot B, which would be equal to 1, 2 dot 2, -1, what we'd obtain, and you can pause the video here to attempt to do the question yourself, but if you're interested in just seeing the answer, what we'd obtain is 2 times 1 plus 2 times -1. And the order in which you multiply them doesn't really matter, because multiplication is commutative. We'd find that this is equal to 2 plus -1. Sorry, -2. We'd find that this is equal to 2 plus -2, which is just 0. And so this is an interesting property that we can deduce from dot products, is that when we have two vectors whose dot product is 0, that means that the two vectors are orthogonal. Orthogonality basically refers to any two vectors who are perfectly perpendicular to one another in 2 dimensions or in 3 dimensions. So that means in 2D or 3D, these two vectors are separated by 90 degrees from one another. To further incorporate this idea of angles, let's introduce the concept of cosine similarity. So cosine similarity is given by this formula. So cosine similarity is given by the formula cosine of the angle theta, and where theta is the angle between vector A and vector B. So cosine of the angle theta is given by A dot B divided by the magnitude of A times the magnitude of B. So you can feel free to attempt to find the cosine theta of the angles between A and B. So if you'll remember from episode 1 of the linear algebra series, we can obtain the magnitudes of A and B using Pythagorean theorem. So first we'll find the magnitude of A. We know that magnitude of A is equal to the square root of 1 squared plus 2 squared, which is equal to square root of 5. And we know that the magnitude of b is equal to the square root of 2 squared plus negative 1 squared, which is equal also to the square root of 5. So, if we now take the dot product of the two vectors, we already know that this is equal to 0. So we know that cosine theta is equal to 0 over root 5 times root 5. So it's just 0 over 5, or 0. And as we know, since these two angles are orthogonal to one another, as we earlier established that dot product of 0 indicates orthogonality, this means that cosine of theta equals to 0. And we know that this occurs at 2 points in the unit circle. We know that this occurs when theta is equal to 90 degrees and when theta is equal to negative 90 degrees, or 270 degrees. And so this proves that two vectors are orthogonal, or that they have a 90-degree angle between one another, when their dot product is 0. Because since the numerator is always going to be 0, that means cosine of theta equals 0, and that has to be one of these two angles. If you have any questions, feel free to leave them in the comments below. Make sure to like and subscribe for more future videos on linear algebra, and thank you. Today we'll be going over the topic of vector projection in the series of Linear Algebra 1. So first I'd like to impart onto you the idea of what a vector projection is. So let's say we have an arbitrary vector, which we'll draw in red, and let's say this is our vector, right? So let's say we have a second vector in blue. It doesn't really matter where it is. And so the idea of vector projection, or a way that I like to think about it, is sort of like the shadow that this red vector casts on this blue vector. So let's say there was a light source here. The red vector would cast a shadow that looks directly downwards onto this blue vector, and so the projected component would be something like this. And so let's make this idea a bit more concrete by introducing the formula. So the formula for vector projection is as follows. So the projection of the vector v onto the vector u is equal to the dot product of u and v. And again, order doesn't matter when you're taking the dot product, so you could be vu divided by the magnitude of vector u squared and multiplied by u. And so this algebraically, while it might be a bit difficult to understand, is what gives us the projected component of v onto u. And so let's take a numerical example. Let's say vector v is 2, 4. And let's say that vector u is equal to 3, 0, just to keep things simple. So let's draw out first vector u. So it's 3 in the x-axis, 0 in the y-axis. So it's a pretty simple vector to draw. This is vector v. Sorry, vector u. Now if we drew out vector v, let's draw it in blue, we find it's 2 in the x, 4 in the y. So we'd have a vector that looks something like this. And so what we're looking for is the amount, or the shadow, so to speak, that this vector casts onto this vector. Now intuitively, visually, because we know this is on the x-axis, the projected component would just be 2, 0, because what you'd find is that this is sort of the shadow of vector v. However, mathematically it's not always that simple, because we don't always have a vector that is lying on an axis. And so let's attempt to solve for uh, the projected component. So if we take the projected component of v onto u as equal to the dot product of u and v, so let's take 3, 0, dot 2, 4. We then divide it by u squared. And a useful trick here is that since we know that the magnitude of u is equal to the Pythagorean theorem, which has a square root, all we need to do to square this is get rid of the square root. So instead of taking component 1 squared plus component 2 squared and that whole thing squared, so 3 squared plus 0 squared, we just take 3 squared plus 0 squared. So we take that this denominator is equal to 3 squared plus 0 squared. And then we multiply this whole thing. This will give us a scalar. We'll multiply the whole thing by the vector u. And so that's a bit interesting intuitively, because that tells us that we're getting sort of a magnitude value, and we're multiplying by the vector we're projecting onto. So it's some scalar multiple of this vector u. And so if we solve this, we'll find that this gives us 6 plus 0 divided by 9 multiplied by 3 comma 0, which is equal to, if you don't know how to reduce fractions, what we have here is 2/3. And so we have 2/3 times 3 comma 0, and we can multiply this into each entry in the vector. What we'll find is that the 3 and 3 cancel, so we have 2 and we have 0. And so that's the same answer we got from this geometric interpretation, but now we have a robust formula that will get us the same answer. And so we find that the projected component is equal to 2 comma 0. I'd like to point out an interesting fact about how this is derived. So what you might notice is that this is very similar to the cosine similarity that we explored in the previous episode. So let's write out the cosine similarity again. We find that the cosine similarity, so cosine theta, equals u dot v over the magnitude of u times the magnitude of v. And so what's different between these two equations? The only difference is that one, we eliminate the magnitude of v and we take the magnitude of u squared instead. And that two, we have a vector that we're multiplying by, which is u. And so intuitively, you might want to take this and expand this a bit so that you can get it looking more similar to this. And so what you'd find is that if we just rewrote it, we'd have projection of v onto u is equal to u dot v over magnitude of u squared, or sorry, just magnitude of u, multiplied by u over magnitude of u. Now if you remember from episode 1, u times the magnitude of u gives us the unit vector. So this is a vector that's pointing in the same direction as u, but it has a unit magnitude of 1. And so what we find here is that we're taking this value, which is the cosine similarity, but multiplied by the magnitude of v. So we have the magnitude of v times the cosine similarity, and then multiplying the unit vector by that. And so intuitively, what you have is you have a vector of length 1 of the vector we're projecting onto, and multiplying it by the component that points in the same direction as that, which is the magnitude of the vector that we're projecting times the cosine similarity of those two vectors. And so if that's a bit confusing, don't worry about it too much. But for the curious amongst you, this is just how we derive this formula. And so finally, let's try another example. So let's take vector u to be equal to 2, 1. Let's take vector v to be equal to 5, 4. And let's draw them out so that we can a bit more easily understand what's going on. So if we draw u in red, we'll find 2 in the x, 1 in the y. So we'll find this vector. And if we draw v in blue, we'll find 5 in the x, 4 in the y. So we'll find this vector. And so we want to project v onto u. What we'll observe is that v is actually longer than u. And so we'll get a resulting vector that's a fair bit longer than the original vector, but it doesn't necessarily matter. What we're projecting onto is the entire line that this vector u can represent. So let's use the formula to get the projection. So we'll take the dot product of u and v divided by the first entry of u squared, so 2 squared, times plus the second entry squared, and then multiply it by u, which is 2, 1. And so what we have is 2 times 5, which is 10, plus 1 times 4, which is 4. We divide it by 2 squared, which is 4, plus 1 squared, which is 5. Then multiply it by 2, 1. And so what we get is 14 over 5 times 2, 1, which is equal to 28 over 5, 14 over 5. And so if we were to draw this out, we'd find 28 over 5 is a bit over, we'd find that 28 over 5 is a bit over here, somewhere in this direction, and then we'd find that 14 over 5 is somewhere around here. And so we'd find that the projected vector is somewhere in this neighborhood. If we're casting a shadow from this vector onto, from this blue vector onto this red vector, it would be in this direction and it would be approximately this long. And so that's all for projection and vector projection. Thank you for watching the video. Please like and subscribe, and be sure to comment if you have any questions or would like me to cover any topics in the future. Welcome back to Easy Academic. In this episode of the Linear Algebra 1 series, we'll be going over the cross product. Now, the cross product is a concept that's a lot more easy to understand in 3 dimensions than in 2. And so we'll start by creating 2 arbitrary vectors, a and b, in 3 dimensions. So we'll have a is equal to a1, a2, a3, and b, which is equal to b1, b2, b3. And so the formula for the cross product is a cross b equals a2 b3 minus a3 b2. This is the first entry. Your second entry is a3 b1 minus a1 b3, your second entry. And the third entry is a1 b2 minus A2 B1. And so the cross product gives us a new vector, whereas the dot product only gives us a scalar value. Now this might be difficult to memorize, and so a trick that I've learned is as follows. So what you want to do is you want to write out A 3 times, A1, A2, A3, A1, A2, A3, and then do the same for B. So B1, B2, B3, B1, B2, B3. And you want to start at A2 and draw these arrows. And you can draw them in different colors if that makes it easier to visualize. So you have these two, which correspond to one another. Let's take a new color, green. These two will correspond to one another. Let's take blue, and these will correspond to one another. And each new color represents a new entry in our final matrix. So our final matrix, A cross B, will be equal to your first entry, which is A2 B3. You always start on the left. So A2 B3 minus B2 A3, which if we compare to up here, you notice it's A2 B3 minus A3 B2. It doesn't matter which order you multiply it, you'll still get the same answer. And your second entry will be A3 B1 minus B3 A1, which you'll notice is the same here. A3 B1 minus B3 A1. And your third entry will be A1 B2 minus B1 A2, which is the same as here. And so you'll observe that this trick works in 3 dimensions as well. So let's compute an example. Let's say A1 is equal to 1, 0, 0. Let's say B is equal to 0, 0, 1. When we take the cross product of these two vectors, we'll obtain, as here, we'll obtain A cross B. A cross B is equal to A2 times B3, which is 0, minus B2 times A3, which is 0. The second entry, A3 times B1, which is 0, and B3 times A1, which is 1. So you'll get 0 minus 1. And you'll find that A1 times B2, which is 0, and B1 times A2, which is 0. And so you'd find A cross B is equal to 0, negative 1, 0. So this is an interesting resulting vector that we've obtained. So what necessarily does it mean? What the cross product gives us is a new vector, A cross B, which we can call C, that is perpendicular to both A and B. So you'll observe that these two are unit vectors, or basis unit vectors, in R3. This is a corresponding negative basis unit vector. So it points in the opposite direction to the standard unit vector, and that's because we did A cross B. The order in which you do your cross product matters, because say we did B cross A, this would be a positive value. And so this represents two things. First, as I mentioned, this gives us a vector that is perpendicular to both A and B. And secondly, if you create a parallelogram, out of A and B in 3 dimensions, with A and B as the side lengths, you'd find that the area of this parallelogram would be given to you by the magnitude of A cross B. And so in this case, the magnitude is 1. And so the area of this parallelogram is 1, as you might be able to as you might be able to intuitively see since the side lengths are both of length 1. I hope this video provided you with an intuitive understanding of what the cross product represents. If you have any questions, be sure to leave them in the comments. Be sure to like and subscribe, and thank you. Welcome to Easy Academic. Today we will be talking about lines in 3D as part of our Introduction to Linear Algebra series. In this video, we will be going over parametric and symmetric forms of representing lines in 3 dimensions. To start, we will go over parametric forms. So, parametric forms of representing lines in 3 dimensions require us to represent the x, y, and z dimension in terms of a new variable. Most often, we call this new variable t. So if we were to represent a line in 3 dimensions, we would denote it as r of t. This is a line function with respect to the variable t. And we set that equal to r naught, which is an initial position variable, or vector rather, that tells us the offset from the origin plus our parameter t times some vector v, which represents information about the direction of the line. And so since this is a parametric equation, we can represent r in terms of its x, y, and z components. So r of t can be broken down into x of t, which is equal to x naught, plus some arbitrary value, let's call it a, times t, where a is the first entry of v, y, which is equal to y naught, plus b times t, where b is the y value in the direction vector, and z, which is equal to z naught, plus c times t. So based on this, we would be given a vector v, or would be asked to find the vector v, such that v is equal to a, b, c. Oftentimes when representing lines parametrically, you might see a different notation for vectors. Vectors might be notated using these brackets, and each entry being separated by a comma. So if you see this notation for a vector, know that it represents the same information as this vector. We will now be going over symmetric forms. So the symmetric form of a line equates x with respect to a, y with respect to b, and z with respect to c in order to represent a line. So to clarify this, we use this general expression. So here we have the general expression x minus x naught over a equals y minus y naught over b equals z minus z naught over c. This is fairly simple to remember, as all you need to do is remember that you subtract your value for x from your given origin offset for x, and then divide by your corresponding value from your direction vector. The symmetric form can be derived from the parametric form if we equate all values of t. So in order to do this, let's rewrite out the parametric form and show you how you can obtain the symmetric form in case you aren't able to memorize this expression. So if we have x equals x naught plus a times t, we can rewrite this by subtracting x naught from both sides, which will give us x minus x naught equals a times t. We can then divide a from both sides. So this will give us x minus x naught over a equals t. As we can see, this is one part of the expression in the entire symmetric representation. Doing the same for y and z would give us y minus y naught over b is equal to t, and z minus z naught over c is equal to t. And we know that since all three of these are equal to t, that means they are all equal to one another. And so that's another way that you can derive the symmetric form. Let's now take a numerical example. So say we are given a point, r naught, which is our initial offset from the origin. And let's say that this point is equal to 1, 2, -1. And let's say that we're given a vector which represents our direction, v, which is equal to 3, -2, 4. Let's first represent this parametrically. So parametrically, we get that x is equal to 1 plus 3 times t. So we got 1 from here and 3 from here, then we multiply by t. We get that y is equal to 2 from here, minus, because we have a minus here, 2 times t. So we get the minus from this second entry in the direction vector. And we get that z is equal to -1 from here, plus 4 from here, times t. So this is how we can represent a line parametrically. Symmetrically, we can either convert this or we can use our general expression. So let's use our general expression to show the relationship in terms of equating all of the sides to t. So again, we can see from our general expression that x minus x naught over a equals y minus y naught over b equals z minus z naught over c. So what we'll do is we'll write this as x minus 1, which is the first x value in r naught, over a, which is 3, equals y minus 2, which is the second value in r naught, over -2, equals z plus 1. And take note that since this is a negative value as the third entry into r naught, if we do minus a negative value, we add. So we have z plus 1 over 4. And this is how we represent our value symmetrically. If you'd like some practice, you could attempt to represent the following point and direction vector symmetrically, just for some practice for the viewer. So let's say we have the point r naught equals 0, 1, 5, and we'll have the direction vector v equal to -2, 1, 3. So you can pause the video before I reveal the answer. So symmetrically, the representation of the answer is x minus 0 over -2, which we got from here, equals y minus 1 over 1 equals z minus 5 over 3. So if you found this video helpful, please be sure to like the video and subscribe to the channel for more useful educational content, as well as feel free to share this video with whoever you think might find it helpful as well. If you have any questions, be sure to leave them in the comments below. Welcome back to Easy Academic. Today we'll be going over planes in 3 dimensions. So in order to understand planes, we must first understand normal vectors. So what is a normal vector? Let's say we have a plane, and this is a plane in 3 dimensions. The normal vector to this plane is perpendicular to this plane at any given point. So that means that there's a 90-degree angle between this vector and the plane. And we'll tend to denote normal vectors using the letter n and using using these triangular looking brackets. So each of the entries that describe this normal vector can be labeled A, B, C, N1, N2, N3, things like that. So now that we understand normal vectors, we could derive how to represent planes in 3 dimensions. So in order to represent a plane in 3 dimensions, we need a point and a normal vector. So say we're giving a point P naught, which is equal to X naught, Y naught, Z naught, and a normal vector. We can take this same normal vector and equals A, B, C. We can obtain the formula or expression for the plane by first taking an arbitrary x, y, and z coordinate we can call r. So r equals x, y, z. We can subtract p naught from r, so r minus p naught, which would give us x minus x naught, y minus y naught, z minus z naught. This is now a vector since we're subtracting 2 points. And then taking the dot product between n and this newly found expression, r minus p naught. So if we represent this using our standard vector notation, we find that the dot product is A, B, C dot x minus x naught, y minus y naught, z minus z naught, which you might recognize these forms of expression from a representation of a line in 3 dimensions, the video for which you can find in the card. So once we further expand on this expression, we find that the equation for the plane exists when we equate this to 0. So once we can now expand this dot product, and we find that A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0 gives us our equation for the plane. More specifically, as you might be able to notice, we can further expand this to get expressions for A, B, and C in terms of the arbitrary x's, y's, and z's, while moving the given x, y's, and z's to the other side of the equation for clarity. So we can have ax minus ax naught plus by minus by naught plus cz minus cz naught equals 0. And rearranging once more, we have ax plus by plus cz equals ax naught plus by naught plus cz naught. We can observe that x naught, y naught, and z naught are givens, and since we know, or we would know, the direction vector ABC, or the normal vector, sorry, ABC, we can express this whole equation as a single variable d. So we finally conclude that the equation for the normal vector, or sorry, the equation for the plane is described as ax plus by plus cz equals d. And in the case where d equals 0, we find that the plane passes through the origin. Let's take a numerical example. So say we're given the point P naught equals 1, 0, 2, and the direction normal vector equal to 2, negative 3, 1. We can use the earlier form ax plus by plus cz equals d we can get to this conclusion by finding the dot product between an arbitrary x, y, and z vector and p and this normal vector. So once again, we have 2 times x minus 1, where 1 is x naught, minus, since we have a negative value here, 3 times y minus 0 plus 1 times z minus 2 equals 0. And here we have the right side still set to 0 because we haven't expanded out. Now when we expand out, we have 2x minus 2 minus 3y plus z minus 2 equals 0. And moving the constants to the right side of the equation, we have 2x minus 3y plus z equals 4. Here we can observe that the coefficients in this equation, 2, 3, and here we have a 1, are equal to the values in the normal vector. So we have that if we're given an equation in its definition of what the plane is, we can find the normal vector by simply taking the coefficients a, b, and c. So here we have 2, negative 3, and 1, if we were to find the equation for the normal vector. So that's all for finding the equation of a plane in 3 dimensions. If you have any questions, feel free to leave them in the comments below, and be sure to like and subscribe. Thank you. Welcome to Easy Academic. In this episode in the linear algebra series, we'll be discussing linear independence of vectors. So what does it mean for a vector or a set of vectors to be linearly independent? Let's say we have a vector A, B, and C. When we want to say that this set of vectors, so we denote a set using these brackets, if we want to say that this set of vectors is linearly independent, that means none of these vectors, being A, B, or C, can be created through any linear combination of any of the other vectors. And so for more information about linear combinations, refer to the video on the card. But formally, if we want to describe that it's impossible to describe any vector in a set with a linear combination of other vectors, how do we do this? In order to formally describe linear independence, we can have an arbitrary constant lambda I. And lambda I can take on any value of any number, which we'll use to multiply by A, B, and C. So let's say lambda 1 times A plus lambda 2 times B plus lambda 3 times C is a linear combination. If we want to figure out whether or not A, B, C, the set, is linearly independent, we check whether or not this linear combination equals 0 if and only if lambda 1, lambda 2, and lambda 3 equals 0. So what does this mean? This means that the only way to combine A, B, and C together to go back to the origin is if we multiply all of them by 0. And so geometrically, how do we interpret this? Let's say in 3 dimensions, we have this. Let's say this is vector A. It's the unit vector along the x-axis. Let's say vector B is the unit vector along the y-axis. In green, we'll say vector 3 is the unit vector along the z-axis. So we have these 3 vectors, A, B, and C, which we can denote A, B, and C. And say we want to describe A in terms of B and C. So we can say that lambda 1 times A is equal to a linear combination lambda 2 times B plus lambda 3 times c. By inspection, the only way that it's the case that we can describe the A vector using B and C is when B and C are both 0 and when A is 0. So say we've multiplied A by 0 and this vector equals 0, B and C must also be 0. Otherwise, it's impossible to describe something on the x-axis using only components in the y and z-axis. So just to recap, broadly speaking, let's say we have an arbitrary number of vectors, which will number v1, v2, all the way through to vn, and these are just all of our vectors, n vectors. And so we want to see whether or not these vectors are linearly independent. In order to check that they're linearly independent, we have to check for ways that we can add them to equal 0. So say these are n-dimensional vectors. All of the entries must be 0 when we add them together in a linear combination. And the only way for that to happen in a linearly independent set of vectors is when we multiply v1 times 0 plus v2 times 0 all the way to vn, which will also be multiplied by 0. Be sure to like and subscribe, and if you have any questions, feel free to leave them in the comment section below. Welcome back to Easy Academic. In this video, in the linear algebra series, we'll be discussing matrices in linear algebra. So first, we must discuss the concept of size of a matrix. So matrix size is often denoted m by n, where m is the number of rows in the matrix and n is the number of columns. So for example, let's say we have a matrix A, which is 2 by 3. That's its size. And we can describe A, for example, as the matrix 1, 0, 4, 5, negative 2, 7. There are 2 rows and 3 columns. Hence, it's 2 by 3. Similarly, let's say we have a matrix B, which is 3 by 1. Let's say this matrix is 6, negative 2, 3. You might notice that this is a column vector, which we can use to demonstrate a vector in 3 dimensions. But once again, there are 3 rows and 1 column. This begs the question, how do we refer to each individual entry in the matrices? So let's take the example of matrix A above and just rewrite it down here. So matrix A equals 1, 0, 4, 5, negative 2, 7. Let's say we want to refer to the element, this element right here. Well, the way we do that is we say lowercase a, and we refer to the item in the ith row in the jth column. So in this situation, the number 4 is in the first row. It's in the first row, and it's in the second column. So let's say we're referring to A1, 2. This would be 4. Similarly, if we were referring to, let's say, the item in the second row, third column, so A2, 3, we would find the second row, third column, and see that we're referring to 7. Now, the topic of matrices introduces the idea of some special matrices. So the first special matrix we'll be walking through is the zero matrix. So this is a matrix with m rows and n columns. The dimension is sort of arbitrary, but the zero matrix is any m by n matrix where all of its entries are zero. So let's take, for example, the 2 by 3 zero matrix. There's only one zero matrix for the 2 by 3 dimensionality. And so we say the 2 by 3 uh, zero matrix is equal to 0, 0, 0, 0, 0, 0. And that's a matrix where every entry is 0 with 2 rows and 3 columns. Let's take the second special matrix, which is the identity matrix. Now, unlike the zero matrix, there is a condition on the dimensionality of the identity matrix, and that is it must be n by n. So that means the number of rows has to equal the number of columns. This gives it the property that it's a square matrix, and on top of that, all of the entries along the top left to bottom right diagonal are all ones. So let's take, for example, the 3 by 3 identity matrix, which is often denoted as I or sometimes as 1. And we'll say that this matrix is 1, 1, 1, 0, 0, 0, 0, 0, 0. This is the 3 by 3 identity matrix. So you'll observe three things. First of all, it's square, so the number of columns has 3 rows and 3 columns. That's the first observation. Secondly, all of the entries on the diagonal, so that is when we take lowercase ij, when I is equal to j, every entry equals 1. And the third property is that every non-1 entry, so every entry that isn't 1 or isn't on the diagonal, is equal to 0. And so the identity has a few important properties. But the most important property that we need to know for now is that if we take any matrix, that is any square matrix, so let's say, for example, we have a 3 by 3 matrix A, and we multiply I by A or A by I, we always get A. So it's similar to the scalar value 1 when you're multiplying any other scalar or vector by it, in that when you take a square matrix of equal dimension to it, multiplying before or afterwards will give you the same matrix that you multiplied it with. That's all for this tutorial on matrices. If you have any questions, be sure to leave them in the comments below, and please like and subscribe. Welcome back to Easy Academic. Today in the linear algebra series, we'll be going over matrix multiplication. So when multiplying matrices, there are a few things we must keep in mind. Firstly is the conformability of the two matrices. So the conformability refers to how the dimensions of the two matrices relate to each other. So the dimension of matrix A must be m by n, and the dimensions of matrix B must be n by some other value, let's call it L. So what that basically means is that if A is m by n, B must be n by L. And then your resulting matrix, let's call that C, will have dimensions m by L. So this might be a bit unintuitive, but let's use an example to illustrate uh, what's going on. So say we have a example matrix, we'll call it Q, and its dimensions are 4 by 3. We have another matrix J, its dimensions are 3 by 6. Your resulting matrix K will have dimensions 4 by 6. And say J had dimensions 2 by 6, you would not be able to get a resulting matrix. And so let's show how matrix multiplication actually works. So let's take a 2 by 2 example. Let's create a matrix A and call it, or give it the values 1, 2, 0, 3, and a matrix B whose values are 4, 0, 1, 2. So if we want to take A times B, what this will look like is 1, 2, 0, 3, 4, 0, 1, 2. So what's happening when we're trying to multiply these two matrices is we essentially go row-wise and we multiply column vectors. So how does this look? The first entry into the resulting matrix is equal to 4, as that's the element here, times the column 1 times 0 plus 1 here times the column 2 times 3. And that's the first column of the alpha matrix. So we take this column multiplied by this value, this column multiplied by this value. That's how we get the first column of the alpha matrix. The second column of the alpha matrix then is obtained by taking 0, multiplying it by the first column. So we have 0 times 1, 0, and 2 multiplied by this second matrix, plus 2 times 2, 3. And this will give us our final output matrix. So what we'll find is that we have 4 plus 2 over 0 plus 3. That's our first column. And 0 plus 4 and 0 plus 6, which in total will give us 6, 3, 4, 6 as A times B. Now an important thing to note is that matrix multiplication is not commutative. So that means A times B is not necessarily equal to B times A. And so to show this, let's show with the given example again. So let's take BA, which would be equal to 4, 0, 1, 2 times 1, 2, 0, 3. And so applying the same sort of algorithm, we have this entry times this column. So we'd have 1 times 4, 1 plus this entry times this column. So 0 times 0, 2. And then the second column, we'd have 2 times 4, 1 plus 3 times 0, 2. From this we'd get 4 plus 0, 1 plus 0 as our first column, and we'd get 8 plus 0, 2 plus 6 as our second column, which yields 4, 8, 1, 8. And so as you can see, BA is not equal to AB. So if you have any questions, feel free to leave them in the comments. Other than that, this is matrix multiplication, and be sure to like and subscribe, and thank you. Welcome back to Easy Academic. In this installment of the linear algebra series, we'll be going over the ideas of row picture and column picture. And so what row picture and column picture aim to do is provide a means of interpreting the general expression AX equals B, where A is a general matrix and X and B are either matrices or vectors. And so you'll remember from the matrix multiplication series that if A is a M by N matrix, X must then be an N by L matrix, and B would be an M by L matrix. We need to figure out a way of interpreting what this matrix multiplication would look like. And so first we'll start with row picture. Row picture allows us an interpretation to view the system AX equals B one row at a time. And so what row picture aims to do is be viewed as a series of intersecting lines and planes. So generally we denote this as, for example, A11 times x1 plus A12 times x2 for all values in A and X. So A1n xn equals B1. So this is for the first row in A for all the values in X and for the first row in B. Similarly, we'd have A21 x1 plus A22 x2 for all the values in A2. And we would get B2, which is the second row in B. And we do this for all values in A, X, and B. So specifically, we go through A and B row by row. We multiply every row in A by the vector or matrix X, and we equate it to the value B. So this might be a bit confusing, so let's work through an example in 2 dimensions to better intuit this. So say we have a matrix A, which is 2 by 2, and we set it equal to 2, -1, 1, 2. We set our matrix X to just be equal to x1, x2, and let's say our B is equal to 3, 8, and we want to solve for the x's here. So an important thing to note is that when we have this representation here, what we're solving for is x. So that is the matrix X. We want to solve for all of the entries, x1, x2, up to xn. So if we write out the row picture interpretation of this, what we have is A11, which is 2, times x1 plus A12, which is -1, times x2 equals the first row of B, which is 3. Similarly, we have A21, which is 1, times x1, plus A22, which is 2, times x2, equals the second row of B, which is 8. And so you'll observe this is a simple series of equations. So we have 2 equations and 2 unknowns, and we can simply solve for either of the x's through either substitution or whatever method you find most appropriate. And so in this case, what we can do is we can rearrange for x1. So let's take this second equation and rearrange for x1. So we'd find that x1 equals 8 minus 2x2 by subtracting 2x2 from both sides. We can then take this value for x1 and substitute it back into the first equation. So we'd have 2 times 8 minus 2x2 minus, so we'll just distribute the negative out here. So we have minus 1x2 equals 3. Expanding this out, we have 16 minus 4x2 minus x2 equals 3. And if we take 16 over to the other side by subtracting both sides, subtracting 16 from both sides, we have negative 4x2 minus x2 equals negative 13. Finally, we have negative 5x2 equals negative 13, which implies x2 is equal to 13 over 5. Now that we have x2, we can solve x1 by substituting back into this expression. So we have that x1 equals 8 minus 2 times x2. And since we know x2 is equal to 13 over 5, we know that x1 is equal to 8 minus 2 times 13 over 5. This is equal to 8 minus 26 over 5. And if we convert 8 into fractional form, the denominator 5, we get 40 minus 26 over 5 is equal to x1, which is equal to 14. So we found that x equals x1, x2, and we found that x1, x2 is equal to 14 over 5, 13 over 5. Now we move on to column picture. What column picture aims to do is to represent the expression ax equals b as a linear combination of column vectors. And so we interpret this column-wise, as is implied by the name column picture. And so using the same example as earlier, let's show what we mean by this. If we use the column, if we use the matrix A, which is equal to 2, negative 1, 1, 2, we have x equal to x1, x2, and our same b equal to 3, 8. And we attempt to solve ax equals b. What we'll find is that 2, negative 1, 1, 2, x1, x2 equals 3, 8. So when we say we want to represent this as a linear combination of the columns of A, what we mean is we want to express this in this sort of way, where we take x1 and multiply it by the first column, and then we add x2 multiplied by the second column, and that linear combination will be equal to b. And so what we represent this as is some scalar multiple x1 of the vector 2, 1. So let's say this is 2, 1 multiplied by some value x1, and we then add the vector negative 1, 2, which would look something like this. And we add those two lines to get the vector 3, 8, which would look something like this. So we would find the scalar multiples x1 and x2 that would allow these vectors to add to 3, 8. So we can do this using a similar method to above, because in my opinion that's what's most intuitive. And so if we distribute the scalars, we'd find that x1 times 2, x1 times 1, this vector plus x2 times negative 1, x2 times 2 is equal to 3, 8. We'd find further that x1, 2 times x1 minus x2 equals 3, and that x1 plus 2 times x2 equals 8. If we took the different approach of multiplying this equation by 2, or let's say by negative 2, we'd find that we obtain negative 2x1 minus 4x2 equals negative 16. And if we then added this equation, so 2x1 minus x2 equals 3, let's say we added that, we'd find that we have 0 minus 5x2 equals negative 13. And again, this implies x2 to be equal to 13 over 5. Substituting this expression back into either of these two will give us the value for x1. So let's take the bottom expression, 2x1 minus x2 equals 3, and substitute in 13 over 5. So 2x1 minus 13 over 5 equals 3. We find that 2x1 is equal to, let's convert this 3 into a fraction in terms of denominator 5. So find that 15 over 3 plus 13 over 3 equals 2x1. And this is equal to 28 over 3. If we then divide both sides by 2, we find x1 to be equal to 14 over 3. And then in total, x equals 14 over 3, 13 over 3, which is the same conclusion from the row picture interpretation. So if you found this video helpful, please like and subscribe to the channel. Be sure to write your comments if you have any questions, and stay tuned for the next episode in the linear algebra series. Welcome back to Easy Academic. This video in the linear algebra series will give a quick introduction to the idea of a matrix transpose. So, broadly speaking, transposing a matrix flips the rows and the columns. So what does that look like? Let's say we have firstly, if we have a matrix A of dimension m by n, this would imply that A transpose has dimensions n by m. So if we take a matrix A with dimensions 2 by 3, A transpose has dimensions 3 by 2. So let's show an example of this. If we have a matrix A, a 2 by 3 matrix A, that is equal to 2, negative 1, 0, 3, 4, 1. The resulting matrix A transpose, which has its rows flipped with its columns, will have dimensions of 3 by 2, and it will now look like this. It will now be 2, -1, 0, 3, 4, 1. That is with dimensions 3 by 2. So you'll notice that the first row now becomes the first column. The second row becomes the second column. So let's introduce some simple properties of transposition. So first, and most importantly, the transpose of A, B, if we're to transpose this matrix multiplication, it's the same as taking B and transposing it and multiplying it by A transposed. So the important thing to note is that we flip the order of A and B, and then we can simply distribute the transpose. And again, it is important that you flip the order because matrix multiplication is not commutative. So B transpose A transpose is not equal to A transpose B transpose. These are not equal. The second property of matrix transposition is that A transpose transposed is equal to A. So essentially, transposing a transpose cancels it out. And so if you have any questions with relation to matrix transposition, feel free to leave them in the comments. Otherwise, please like and subscribe, and stay tuned for more episodes in the Introduction to Linear Algebra series. Welcome to Easy Academic. In this episode of the Introduction to Linear Algebra series, we'll be discussing elementary matrices. So elementary matrices are matrices that allow us to apply the 3 row operations. So what are these row operations? The first row operation is swapping rows. So if we have any matrix A, a legal row operation that we are allowed to perform is swapping 2 of the rows within A. The second row operation is scaling any row by some value, as long as that value is not equal to 0. The third row operation is adding a scalar multiple of one row to another. And so what does that look like in terms of elementary matrices? Let's start with swapping rows. Now some important context about elementary matrices is that all elementary matrices are based on the special matrix case of the identity matrix. And if you're curious about the identity matrix, feel free to go back to my video about matrices. So if we have an identity matrix, which is denoted as I, or in some cases 1, let's say we have a 3 by 3 1 matrix. So this would be equal to 1, 1, 1. So if we took this identity matrix and we had another matrix A, which had, let's say it has arbitrary entries, A, B, C, D, E, F, G, H, I. If we wanted to swap any 2 rows in A, we could multiply by the corresponding elementary matrix which swaps those rows. So if we transform the identity matrix I into the elementary matrix E of type 1 meaning it swaps rows, we simply take I here and then we swap two of its rows. So say we swap row 1 and row 3. We would have row 3 as the first one, so 0, 0, 1. Row 2 would remain unchanged, so 0, 1, 0. And row 1 would now be where row 3 originally was, so 1, 0, 0. Then, multiplying that by this new value for E, multiplying that by A, would swap the first and third rows in A. So let's demonstrate this. E times A equals 0, 0, 1, 0, 1, 0, 1, 0, 0 times A, B, C, D, F, G, I. So if you remember back to the video about matrix multiplication, here's what we'll get. The first column will be A times plus D times the second column plus G times the third column. The second column will be B times the first column plus E times the second column plus H times the third column. And the third column will be C times the first column in E plus F times the second column in E plus I times the third column in E. So if we now combine these values, we have 0, 0, A is one value plus 0, D, 0 plus G, 0, 0. And this is one column. We have 0, 0, B plus 0, E, 0 plus H, 0, 0. And this is the second column. In our third column, we have 0, 0, C plus 0, F, 0 plus I, 0, 0. And this is our third column. And so finally, we have G, D, A, H, E, B, I, F, C. And so if we now compare this to the original matrix A over here, we see that they are the same matrix except that the first and third columns are swapped. So this is a demonstration of the elementary matrix swapping rows. We can now show an example of the elementary matrix scaling rows. So now that we have a bit more intuitive of an understanding of the role the identity matrix plays, I'd like for you to pause and assume what would happen if I asked you to take this matrix A and try and find the elementary matrix that would scale the second row by 3. So as you might have guessed, if we take the identity matrix and we attempt to transform it into the corresponding identity matrix, what we'd find is that we have 1, 1, 1, And in order to take the second row and multiply it by 3, in terms of A, we simply do that transformation on the identity matrix. And so this whole matrix gets turned into 1, 3, 1. And so now what does E times A look like? This looks like 1, 3, 1 times A. And again, multiplying the matrices, you find A is 1, 0, 0 plus D 0, 3, 0 plus G 0, 0, 1. It's one column. Find B 1, 0, 0 plus E 0, 3, 0 plus H 0, 0, 1 is the second column. We find C 1, 0, 0 plus F 0, 3, 0 plus I 0, 0, 1 is the third column. This is equal to, we can do this a bit faster now that we're getting used to multiplying matrices. We have A, 3D, G as our first column. We have B, 3E, H as our second column. And we have C, 3F, I as our third column. And so as you can see, scaling the second row of the identity matrix by 3 to get the elementary matrix E, then multiplying E by A scales the second row of A by 3. Now the third type of elementary matrix allows us to add a scalar multiple of one row to another. So to keep it simple, let's take again our example matrix A. And let's say we want to add 1 times row 2 to row 3. So again, you can pause and think what we'd have to do to our identity matrix to enable this to allow us to multiply E by A to get there. So again, if we have our identity matrix as 1, 1, 1, in order to transform it to an appropriate E, where we add 1 times the second row to the third row, what we'll do is we'll take our first row and leave it as it is. We'll take our second row and leave it as it is. But for our third row, we'll add the second row to the third row. So we'll find we have 0, 1 plus 0, which is 1, and then 0 plus 1, which is 1. So this is our matrix E. So let's now multiply by A to show that this property, again, still holds. So E times A equals 1, 0, 0, 0, 1. And then we still have our original A. And so in order to get the first row, again, we'll multiply A by the first column in E. So 1, 0, 0. Add D times 0, 1, 1. Add G times 0, 0, 1. That's our first column. Again, we'll take B times 1, 0, 0. E times 0, 1, 1. And G times 0, 0, 1. And again, we'll take our third column, C times 1, 0, 0, F times 0, 1, 1, and I times 0, 0, 1. And finally, this one's a bit more complicated to attempt to visualize, so let's do it in two steps. This is A, 0, 0 plus 0, D, D plus 0, 0, G. Second column gives us B, 0, 0 plus 0, E, E plus 0, 0, G. And our third column gives us C, 0, 0 plus 0, F, F plus 0, 0, I. And finally, we obtain EA is equal to A, 0, sorry, is equal to A plus 0, 0, 0 plus D plus 0, and D plus G. We have B plus 0 plus 0, 0 plus E plus 0, and E plus G. I'm sorry, this is supposed to be H. So this is actually H. So what we have actually is E plus H. And then here we have C, F, and F plus I, which we'll observe is the same as D, E, F plus G, H, I. So the second row from the initial third row in A. So I hope this video was helpful if you were looking to attempt to understand elementary matrices. If it was, be sure to like and subscribe. And if you have any questions, be sure to leave them in the comments below. I'll try to help you out with those. Thank you. Welcome to Easy Academic. Today in the linear algebra series, we'll be going over Gaussian elimination. Now, Gaussian elimination extends from the idea of elimination matrices. But to understand Gaussian elimination, we must first understand what a pivot is. So what is a pivot? There are three important elements of a pivot. First is a pivot position. So the pivot position in each row is the first non-zero entry when you're reading the row in the matrix from left to right. So say we have any row R, call it Ri, in any matrix. When you're reading this row from left to right, the first value in that row that is non-zero is the pivot position. So Ri is first non-zero entry. So when we use Gaussian elimination to turn a matrix into something called row echelon form, the pivot lies to the right of the pivot in each previous row. So say we have the first row. In the second row, the pivot must be to the right of where the pivot is in the first row. So say, for example, the pivot in row 1, the pivot is the first element. In row 2, the pivot must be some value greater than 1 in terms of which element it is. Must be the nth element where n is greater than 1. So then we have the pivot element. So with the pivot position, all we've clarified is that it's some non-zero entry. However, the pivot element is what that value actually is. This can be any value. However, in reduced row echelon form, which is an extension of row echelon form, we often find that this value is 1. Finally, we have the pivot column. So the pivot column represents the entire column where any given pivot is. Now this is important because each pivot column is linearly independent. So what does this tell us? This tells us that if we create a new matrix that only contains all of the pivot columns that are in our original matrix, we can, in theory, create the same number of linear combinations as using the original matrix. But now we have less information that's being used to get to the same number of possible linear combinations. So now that we understand what a pivot is, we can actually perform Gaussian elimination to create a matrix in row echelon form, sorry. So there's a checklist of things we want to do in order to accomplish row echelon form. So first, we want all 0 rows, so that is all rows containing only zeros. We want all of these rows to sit at the bottom of the matrix. Secondly, we want to make sure that the property above here with the pivot element, or sorry, with the pivot position is maintained. That is, we want every non-zero in any given row to be to the right of the pivot in the previous row. And third, we want every entry that's below each pivot to be a 0. So let's work through an example of how we'd create a row echelon form of a matrix. So here we have the matrix A, which is a 3 by 4 matrix. And the primary idea of transforming a matrix to a new matrix in row echelon form using Gaussian elimination is based on the idea of matrix elimination, which you can find a video for relating to elimination matrices in the card. Now, in the elimination matrix video, we use the example of square matrices. However, uh, elimination in matrices and matrix transformations can be done on non-square matrices as well. The properties all still hold. So you can swap any two rows, you can add a scalar multiple of one row to another, and you can scale any row by a value. So step one in this example is, for convenience, we're going to scale the first row. We're going to take it and we're going to transform it to 1/2 of its original value. And that is so that we can get this first entry to be equal to 1. So that will look like 1 over 2, 0, 3 over 2. The next step is to attempt to eliminate this value that's directly below this pivot. So it's important to identify that in the first row, this 1 is the pivot. And so in order for the pivot in the second row to be to the right of the first row, we must eliminate this value that's directly below it. So in order to do that, we're going to transform it by taking row 2 and transforming it to row 2 plus a scalar multiple of some other row. So we're going to take row 2 and we're going to say plus negative 1 times 4 times row 1, which more simply can be written as row 2 minus 4 times row 1. So what this looks like is row 1 again remains unchanged. Then in row 2 we subtracted 4 here. We then have negative 4 times negative 1 over 2, which is positive 2, so we add 2 here to get 5. This remains unchanged. Then we have negative 4 times 3 over 2, which is negative 6. So we have 7 minus 6, which is 1. And then the bottom row remains unchanged. Again, we want to make sure that all of the values below each pivot are 0. So since we've identified this 1 to be a pivot, this 6 must also be a 0. So we'll do the same thing with the third row, which is row 3 will be transformed into row 3 minus 6 times row 1. And here again we observe that row 1 and 2 are unchanged. And since we've now subtracted 6 here, we then do negative 6 times negative 1 over 2. So we get plus 3. This is also 5 then. We do negative 6 times 0, so this is unchanged. And then negative 6 times 3 over 2, which is a negative 9, so this is 0. We now observe that in the second row, this value is a pivot. So here we can scale this to 1, like we did with the original first value, but since we observe that the value directly below it is the same, it's a lot more convenient to just keep this 5 as it is and subtract it directly. So we'll transform the third row again by doing the third row minus the second row to eliminate this value and make all values below this pivot equal to 0. And so again, the first row remains unchanged. The second row remains unchanged. In the third row, we have 0 minus 0, we have 5 minus 0, we have 1 minus 1, and then we have 0 minus 1, which is negative 1. And so this is our final matrix in row echelon form. So we observe that the pivots are 1, 5, and negative 1, and we can write this as A tilde to indicate that this is the original matrix A in row echelon form. Let's identify a useful property that's been obtained by finding the row echelon form of this matrix. So because we know that these three are the pivots, that means that there are 3 independent or linearly independent columns. And so what that means is that the rank of matrix A is 3. And so by using Gaussian elimination to find matrix A in row echelon form, we're able to obtain the rank of matrix A in a pretty concise way. And the rank can tell us some other things which we'll discuss further in future episodes. But if you're interested in learning about rank of a matrix, be sure to check out the video available in the card. If you have any questions, feel free to leave them in the comment section below. Otherwise, like and subscribe if you found this helpful, and thank you. Welcome back to Easy Academic. In this episode of the Linear Algebra series, we'll be discussing reduced row echelon form. Now this is an extension of the prior episode where we talked about Gaussian elimination and row echelon form. But there are 2 main factors that characterize a reduced row echelon form as compared to a row echelon form. So as we discussed in the prior episode, the pivots are very important. But the first property of reduced row echelon form is that all the pivots are 1, as I alluded to in the previous episode. And it's very important that you understand Gaussian elimination and standard row echelon form before we learn about reduced row echelon form. So if you're curious about that, be sure to check out the video on the card. Now, the second property that's very important is that the zeros above every pivot are 0. Similar to row echelon form where the values below every pivot are 0, but as an extension, now if the value for the pivot is not at the top row of the matrix, all values above it must also be 0. So let's look at an example matrix that we've already converted to row echelon form. So this is the matrix from the previous episode, which we've called A tilde, that we already converted to row echelon form. So there's some important things of note when making comparison about why this isn't only in only in row echelon form and not in reduced row echelon form. So firstly, you'll observe that these two pivots, 5 and -1, are not equal to 1. So because they're not equal to 1, that means that this is not in reduced row echelon form. Additionally, these values, all of these other values that aren't the pivots, are all non-zero. So because of these reasons, this is only in row echelon form and not in reduced row echelon form. So with that being said, let's convert this into reduced row echelon form. So first what we'll observe is that the second row, the first pivot, is 5. So we can simply scale the second row. So we can take R2 and transform it to 1/5 of R2. So this will give us the first row is unchanged. The second row is now scaled by 1/5, and the third row is unchanged. Similarly, we can take the third row and scale it by -1. We'll find again the first and second rows are unchanged. And the third row just has this value converted. Now that all our pivots are 1, we can clear out values that are non-zero, that are supposed to be non-zero, in rows above by using rows that are below them. So first we'll clear out the non-zero values above this pivot 1, which is this one. So what we'll do is we'll take 1/2 of row 2 and add it to row 1. So this transformation will look like row 1 being converted to row 1 plus 1/2 row 2, which will look like 1, 0, and then we have 1/2 divided by 2, so 1/10, and then 1/10 plus 3/2. And the second and third rows remain unchanged. What we now need to do is clear these non-zero values above the pivot. So what we'll do is we'll multiply this value by whatever is needed to eliminate the values above it. So in row 2, we'll transform it by, so in row 2 we'll transform it by taking it and subtracting 1/5 of row 3, which looks like this. And then for the final matrix in reduced row echelon form, we subtract 16/10 of row 3 from row 1, which looks like this. And so this is our final A in reduced row echelon form. So now that we have our matrix in reduced row echelon form, we can identify these things called basic variables or leading variables and free variables. So leading variables are any column that has a pivot. So this column, and this column are all leading variables. The free variables are the columns that do not have a pivot. So this column, I do that in a different color. So with leading variables, when you solve to identify leading variables, you write them in terms of the free variables. Whereas the free variables can take on any value. This is in the case that infinitely many solutions are present when you have a matrix equation. So that's all for this episode in the linear algebra series. If you have any questions, feel free to ask them in the comments below. Otherwise, if you found this useful, please like and subscribe to the channel. Welcome back to Easy Academic. In this episode in the linear algebra series, we'll be discussing the rank of a matrix. So what the rank of a matrix is, it describes the number of pivots in a matrix. So if you're unfamiliar with what a pivot is, be sure to refer to the video in the card on Gaussian elimination. So the rank of a matrix is equal to the number of pivots. And this is also equal to the number of linearly independent rows, which is also equal to the number of linearly independent columns. So what does this mean geometrically? Let's first take the example of a full rank matrix. Let's first take the example of a full rank matrix. So a full rank matrix is when the number of pivots is equal to the number of columns in your matrix. Geometrically, this means that the rows of your matrix span the entirety of the dimension of your matrix. So say for example you have a 3 by 2 matrix. That means you have 2 columns in this matrix. If you have 2 pivots, this implies that both of the columns in your matrix can span 2 dimensions. Taking some more specific examples, a rank of 2 represents a plane. More specifically, this is a plane through the origin. A rank of 1, as you might imagine, is a line. Now we have this special case of a rank 0. What this represents in a matrix is that we have no pivots, which means that all the rows in that matrix are 0 rows. So all the entries in all of those rows are 0. In this special case, the span of your matrix is 0, which means that any linear combination of rows in the matrix always result in 0, no matter what you multiply each row by. So this has been an overview of a rank of matrices in linear algebra. If you have any questions, feel free to ask them in the comments below. Otherwise, if this was useful to you, please like the video and subscribe to the channel for more content. Welcome back to Easy Academic. In this episode of the linear algebra series, we will be going over 2x2 and 3x3 determinants. So first we'll start with 2x2 determinants, a shortcut for them, and then we'll go over Sarrus rule for 3x3 determinants. So let's say we have a matrix A. We'll define it arbitrarily as A, B, C, D. If we wanted to find the determinant for the matrix A, which is denoted as det A, or determinant of the matrix itself, we could use the simple formula that is A times D minus B times C. So that is to say, we multiply this entry, that is the entry in the top left, by the entry in the bottom right, and subtract from that the entry in the top right times the entry in the bottom left. And this is simply how we'd get the determinant for a 2x2 matrix. So let's show an example. Let's say that matrix B is equal to 3, 2, 1, 5. If we wanted to take the determinant of B, which is equal to the determinant of this matrix, we'd find that this is equal to 3 times 5 minus 2 times 1, which is equal to 15 minus 2, or 13. The geometric interpretation of the determinant of a matrix A is given by the area of the parallelogram which is spanned by its columns. So in this example with B, we have two columns. Column 1 of B, which will denote C1, is equal to 3, 1, while column 2 is equal to 2, 5. These two columns constitute two vectors in 2 dimensions. And so if we were to span a parallelogram using both of these vectors, the area of that parallelogram is what the determinant tells us. And the determinant can be negative. A negative determinant here tells us the orientation of the two vectors. So if we flip the two vectors around, then you'd get the inverse. So for example, if we say vector B prime equals 2, 5, 3, 1, the determinant would be negative of the determinant of B. So let's show this. Determinant of 2, 3, 5, 1 equals 2 times 1 minus 3 times 5. And intuitively, you see that these two entries have been flipped. So since we're subtracting, we would get the negative value. So we'd get 2 minus 15, which is negative 13, which, as you can see, is the inverse. So now that we know the trick for multiplying or finding the determinant of 2x2 matrices, we can now show Sarrus rule for 3x3 matrices. So let's define a new matrix A, which is the 3x3 matrix A, B, C, D, E, F, G, H, I. And again, this is an arbitrary matrix, just to show the role of each entry. Sarrus rule says that we can rewrite A and add the first two columns to the right of A. So that sounds a little confusing. Let me draw this out so that it becomes a bit more clear. So we have the original matrix A, and then to the right of it, we can sort of partition A original, and then we redraw the first two columns. So this is the representation of Saru's rule. So what we can do now is we can draw these arrows that will indicate to us what we have to multiply. So first we draw these three arrows through these diagonals. And these three arrows tell us the first three terms that we are going to use when we're finding the determinant. So part of determinant of A is given to us by A times E times I plus B times F times G plus C times D times H, as we can see from these arrows. Now we need to draw three more arrows. So we start this arrow from the left of the original matrix A. So we have CEG, AFH, BDI. Now this second part of the determinant is subtracted from the first part. So what we have is this first part, this original part. From it we subtract C times E times G plus A times F times H plus B times D times I. And this is Saru's rule. So let's show a numerical example of utilizing this rule. So let's say we have a new matrix B, which is equal to 2, -1, 3, 0, 4, 1, -2, 5, 2. Now you could memorize this whole expression, but it's easier and more intuitive in a lot of ways to just draw out the two columns. So what we have is 2, -1, 3, 0, 4, 1, -2, 5, 2, and then our two new columns, 2, -1, 0, 4, -2, 5. And then we can once again draw out our arrows. And so what this tells us is that the determinant of B is equal to 2 times 4 times 2 plus -1 times 1 times -2 plus, we see there's a 0 in there, so we can just disregard this last term entirely. Then from this we subtract 2 times 4 times -2 plus 2 times 1 times 5. And again we see that this 0 just negates this final term. And so from this we get 16 plus 2. This is the first part. And from it we subtract -16 plus 10. So this term gives us -6, which we then multiply by -1. So we get 18 plus 6, which is equal to 24. And so the determinant of B is 24. And now for geometric interpretation of B, again, we have three columns, but instead of the three columns spanning a parallelogram, since this is in 3-dimension, we span a shape called a parallelepiped, and this is essentially the 3-dimensional analog of a parallelogram. And again, you get a certain sign that dictates the orientation of the three columns. And again, if you swap any two of the columns, you invert the sign of the volume of this parallelepiped. So if you found this video helpful, Please be sure to like the video and consider subscribing to the channel. If you have any questions on the concept, please feel free to drop them in the comments below. Thank you. Welcome back to Easy Academic. In this episode in the linear algebra series, we'll be discussing properties of determinants. And so if you're unfamiliar with determinants, you should consider looking at this video in the card, as it will give you an introduction to what you need to know about 2x2 and 3x3 determinants. Otherwise, first we'll start with the multiplicative property of determinants. So the multiplicative property of determinants tells us the determinant of the product of two matrices is equal to the determinant of the first matrix times the determinant of the second matrix. So say we have a matrices A and B, the determinant of this value is equal to the determinant of A times the determinant of B for any square A and B, assuming A and B have the same size. So let's show a numerical example of this. So let's say we have a matrix A, which is 2x2, and it's 1, 2, 3, 4. And we have a matrix B, which also must be 2x2. We'll set its values to 2, 0, -1, and 5. If we find the matrix product of these, we find AB is equal to 1, 3, 2, 4 times 2, -1, 0, 5. And again, if you need a refresher on matrix multiplication, you can find a link to that video in the description as well, or somewhere in the associated playlist. Find that the first entry, the first column into this matrix is equal to 2 times the first column plus -1 times the second column. And the second entry into this matrix is equal to 0 times the first column, which will be 0, plus 5 times the column 2, 4. And so we find that this is equal to 2, 6, plus -2 and -4. The second column is simply 10, 20. And this in sum is equal to 0, -2, 10, 20. Sorry, 0, 2, 10, 20. So if we take the determinant of this, we'd be taking the determinant of 0, 10, 2, 20. And this gives us 0 times 20 minus 10 times 2, which is -20. However, if we took the determinant of A, which is the determinant of 1, 2, 3, 4, and from this we get 1 times 4 minus 2 times 3, we get 4 minus 6, which is -2. If we then take the determinant of B, which is equal to the determinant of 2, 0, -1, 5, we'd find that we have 2 times 5 minus 0 times -1. And there we get 10. So the determinant of A times the determinant of B, and remember, the determinant gives us two scalar quantities, is -2 times 10, which is equal to -20, which you'll observe is the same as the determinant of A times B. The second important property to show is the transpose property. So quite simply, all this says is that the determinant of A is equal to the determinant of A transpose. So again, let's take a simple 2 by 2 matrix, 1, 2, 3, 4, and find its determinant. So the determinant of 1, 2, 3, 4 is equal to 1 times 4 minus 2 times 3. For this, we get 4 minus 6, we get negative 2. If we then take A transpose, swapping the rows and the columns, we get 1, 2 as the first column, and 3, 4 as the second column. So if we take the determinant of A transpose, we obtain the determinant of 1, 3, 2, 4. And we get, again, 1 times 4 minus 3 times 2, which we'll observe again is 4 minus 6, which is negative 2. Lastly, I'd like to show the effects of the row operations that we use in Gaussian elimination on the determinant. So first, what happens when we swap rows? Swapping rows gives your determinant the inverse value. So say, for example, you have the matrix A, which is equal to 1, 2, 3, 4. If we swapped row 2 and row 1, so if we swapped these two rows to give us this new matrix A prime, which is equal to 3, 4, 1, 2, the determinant of A would be equal to negative the determinant of A prime. And so let's show this. We know the determinant of A to be negative 2 from the earlier example here. So let's compute the determinant of A prime. So the determinant of A prime is equal to the determinant of 3, 4, 1, 2, which is equal to 3 times 2 minus 4 times 1. From this, we get 6 minus 4, which is equal to 2. Now, as you'll observe, 2 is a negative of negative 2. So what happens if we scale any given row I by some value, let's call it k. So if we scale a row I by a constant k, we multiply the whole determinant by k. Let's take our original example of 1, 2, 3, 4, and transform its second row by multiplying it by 3, which will give us the new matrix A prime, which is equal to 1, 2, 9, 12. We note the determinant of this to be equal to negative 2. But if we now took the determinant of A prime, we'd find we're taking the determinant of 1, 2, 9, 12, which gives us 1 times 12 minus 2 times 9. This gives us 12 minus 18, which is equal to negative 6. And we know that negative 2 equals some value k times negative 6. We know that negative 2 times k equals negative 6. And pretty intuitively, you can tell that k equals 3. Finally, what happens if we add a scalar multiple of one row to another. Well, in this case, the determinant doesn't change. So if we have again our matrix A equal to 1, 2, 3, 4, and say we add 2 times the first row to the second row, which would give us 1, 2, and then 2 times the first row, so 5, and then 8, we'd get the exact same determinant as the determinant of A. Now this may seem a bit unintuitive, but let's show it with this example. So we know that the determinant of A is negative 2. If this is A prime, we show that the determinant of A prime, which is equal to the determinant of 1, 2, 5, 8, is equal to 1 times 8 minus 2 times 5. This is equal to 8 minus 10, which is negative 2. So as you can see, the determinants of A equals the determinant of A prime. And so to recap, the effect of the 3 row operations are as follows. Swapping 2 rows multiplies your determinant by negative 1. So if you have a matrix A, if you've obtained its determinant and then swap 2 rows, the determinant of the new matrix is negative 1 times the original matrix. If you scale any row I by some value k, you scale the determinant of that matrix by k. And if you add any row, or any scalar multiple of any row, to any other row, it has no change on the determinant. And so these are the properties of determinants in matrices. Feel free to comment if you have any questions on the concept below. Otherwise, if you found this concept useful, please like the video and subscribe to the channel. Welcome back to Easy Academic. In this video in the linear algebra series, we'll be discussing inverse matrices, specifically inverse matrices for 2 by 2 matrices. So the formula for an inverse matrix of A, so let's first define A as A, B, C, D. The formula for the inverse matrix of A, which we denote as A to the negative 1, is given as 1 over the determinant of A multiplied by D, negative B, negative C, A. So let's show an example. So firstly, we need to find the determinant of A. And if you're unfamiliar with how to find the determinant of A, feel free to refer to the determinant video in this linear algebra series, which is available in the playlist link in the description or in the card. So let's say our matrix A is equal to 3, 4, 5, 6. If we take the determinant of A, which is equal to the determinant of 3, 4, 5, 6, we find that the determinant is equal to 3 times 6 minus 4 times 5, which gives us 18 minus 20, which is equal to negative 2. Now that we have the determinant of A, we can obtain A inverse. So we know that A inverse is given by 1 over the determinant, which in this case is negative 2, times D, which in this case is 6, negative B, which in this case is negative 4, negative C, which in this case is negative 5, and A, which in this case is 3. And this gives A inverse to be equal to negative 3, 2, 5 over 2, negative 3 over 2. An important thing to note is that when the determinant is equal to 0, the matrix is not invertible. So why is this? This is because we have to take 1 over the determinant of our matrix A. So if this value is equal to 0, this implies that we have 1 over 0, which is an indeterminate form. So we can't have a value, we can't divide any number by 0. Therefore, you can't have an inverse matrix, since you'd be multiplying 1 by, you'd be dividing 1 by 0. If you found this video helpful in explaining the concept, please feel free to like the video and subscribe to the channel. Otherwise, if you have any questions, please leave them in the comments below. Welcome to Easy Academic. In this episode in the linear algebra series, we'll be talking about solving the A equals CR system. So in order to solve the A equals CR system, you must first understand how to reduce a matrix A into its row echelon form or reduced row echelon form. So the essence of solving the A equals CR system is finding matrices C and R based on the pivots in the row echelon form or reduced row echelon form of A. So say we have a matrix A and we've converted into a row echelon form, which can take on the form of some matrix with entries such as this. Doesn't really matter what the entries are, but just for illustration's sake, we say that these x's are the pivots. Each of these columns with the corresponding pivot will be used to transform into the matrix C. So C is a matrix of columns where each column is from the original matrix A, not the row echelon or reduced row echelon form A, but the original matrix A, where the pivots exist in the row echelon form. So this is the column of pivot 1, which will denote column P1, the column of pivot 2, and the column of pivot 3. And if this is unclear, we'll work through an example later in the video. And then to find R, we find all of the non-zero rows in row echelon form. Now, unlike finding C, R is directly related to the row echelon or reduced row echelon form. So R is simply it's a singular, it's a matrix comprised of the rows of the, it's a matrix comprised of the rows in row echelon form that are non-zero. So this is row 1, which is non-zero, row 2, which is non-zero, for however many non-zero rows there are. So let's work through an example to illustrate how to find C and R in the system A equals CR. So let's say we have the matrix A, which is a 4 by 5 matrix. Our first step would be to reduce this into row echelon form. So if you'd like to attempt to solve this by yourself, you can pause the video here before I reveal the row echelon form of this matrix. So this is the row echelon form of the matrix A. We can make a few key observations. First, we observe that there are two pivots in the first and second row. And second, we observe that these two rows are both zero rows, meaning they will not be included when we find our final matrix R. And so first we'll find the matrix C. And again, we know that the pivots are in column 1 and column 3. So that means we find column 1 and column 3 in the original matrix A, and these two columns constitute the columns of C. So we have C is equal to 1, 2, -1, 0, 0, 1, 1, 1. So this is our matrix C. R now is taken directly from the row echelon form of the matrix A. And so since we have two rows here that are both zero rows, we disregard them from the matrix R. And so R is constituted of 1, 2, 0, 3, 1, and 0, 0, 1, 1, 5. And so what this means is that A can be represented as the multiplication of the matrices C and R. Let's demonstrate this by multiplying out C and R. So if we take C multiplied by R, we obtain this. So our final matrix should be of dimension 4 by 5. And so the first entry into this matrix is 1 times the first column. And then 0 times the second column, so we'll leave that as 0. The second entry is 2 times the first column. And again, 0 times the second column. The third entry is 0 times the first column and 1 times the second column. Fourth entry is 3 times the first column plus 1 times the second column. And the final column is 1 times the first column plus 5 times the second column. Expanding this out, we have the first column is 1, 2, negative 1, 0. Second column is 2, 4, negative 2, 0. Third column is 0, 1, 1, 1. The third column is 3, 7, negative 2, 1. And the fifth column is 1, 3, 4, 5. Now if we compare this to our original matrix A, we find that this matrix is indeed equal to our matrices C and R multiplied by one another. So this concludes the Introduction to Linear Algebra series. If you have any questions about this concept in particular or any concept in the series, please feel free to leave them in the comments below. Otherwise, if you found this useful, please like the video and consider subscribing to the channel. Thank you.